Grade 12 Functions, Section 2.4. Today we'll be talking about how we can use rates of change to create a graphical model. So let's look at this example right here. We have two rates of change, and as you can see, as time progresses, the speed increases. Now one thing to notice here is that we compare between these two models. We'll see that here the speed is increasing at a linear rate. That means that, let's say I had an example where this was a person walking, for example. That person would be walking at the exact same speed throughout until they reached this point right here, where they would be standing stationary, and then the speed would be decreasing at the exact same rate. Now, obviously, this is kind of unrealistic, but let's look at the other example where the speed actually accelerates as we continue up, right? So that means that the rate of change, so the slope, would be different at each point throughout. And then the person stays stationary again, and then they again decelerate, where the slope would be again different at each point throughout. So these are two examples that you can see. Now, some other things to note about these graphs: we look at time and speed, and we're looking at time being our independent variable and speed being our dependent variable. And with that, let's continue on then to another example of how rates can be represented graphically. So in this case, we can see the height of the graduated cylinder compared to time, and the height of a beaker compared to time. So in both cases, these are both linear. And what does that mean? That means that the rate of change is constant in both these cases. So again, we're looking at height compared to time, but in a flask, we can see that the height actually changes compared to time, right? So in this case, this would no longer be constant, and the rate of change would differ. The slope at each point would differ comparing to the point in time we're looking at. Okay. Now we also have another example here where it's formed with two pieces, right? So we see there's actually a break in this graph. Not a break, sorry. But we see there's actually a change in this graph at this point right here. But up at the points leading up to this graph, it's a constant rate of change of deceleration. And here as well, it's a constant rate of change of the deceleration, but it changes at this point right here. So that's another example of how rates of change can be shown graphically. And in this case, we're looking at speed dependent on time. So let's go to summary then. So in a problem that involves movement, the graph will show us displacement, distance, height, or depth versus time, which we've seen in all three examples. We have speed, we have height shown throughout time, and we also can show distance. And these are the dependent variables, and time is always the independent variable. So therefore, the rate of change in these relationships is speed. So we can see then that speed is delta d over delta t. So it's always the absolute value that is shown here, and it's the change in displacement over the change in time. So in the graph, the magnitude of the slope of the secant line will determine the average speed of the corresponding interval. Okay, so basically what we're saying here is that if you took these 2 points, for example, and you formed an average rate of change here, the size, or like the magnitude of the average rate of change, again, we're using magnitude here because we take the absolute value, we're using the magnitude here, and it would tell us the average speed on that interval. And if we took the slope of a tangent line, so let's say we took it at a specific point, for example, this would be a great place we can use the tangent line. So let's say we took the tangent line here, that would tell us the speed at that point, or the instantaneous rate of change. As a result, observing how the slopes of the tangent lines change at different points in the graph give you insight on how speed changes over time. So again, now we have some examples, as we discussed previously, when to know that the rate of change or speed is constant. So if it's an increasing line, right, the key thing being here, if it's a line that's increasing at a constant rate, that means that the displacement increases as time increases. If the line is decreasing, that means the displacement decreases as time increases. And if it's a straight line, that means there is no change in displacement as time increases. So this relates to our first example we saw here, where we talked about a person walking. So in this case, it's increasing at a constant rate, then the person is standing, and then it's decreasing at a constant rate. Okay. Then, when the rate of change or displacement in speed is variable, an increasing curve indicates that the displacement increases as time increases. So remember when I broke it down into little slopes? That's what they're doing here. They're looking at little slopes for the different points in time. And they're telling us that means that the displacement increases as time increases. And similarly here, the speed is decreasing as the time increases. Okay. Lastly, a decreasing curve indicates that displacement decreases as time increases. Basically, we're seeing here that as time is passing, as time is increasing, our displacement is getting lower and lower and lower. But the rate at which this is occurring is different each time, and that's why we have our 3 different slopes. And in theory, it can be broken down to even many, many more small slopes, right? Because we're looking at each little point in time. And the other thing that could happen is that the speed is increasing as time increases. Okay, so now we have example 8, and the following graph shows speed versus time, and we're going to match each graph with the description given below. So A matches to A, B matches to C, C matches to D, and D matches to B. So a couple things to consider here. How do we know how to interpret these graphs? The first thing you're going to want to do is look at the slopes, break it down into little slopes, and see how these slopes are changing. Right? You can imagine that in this case, for graph A, for example, the value of this slope will be larger than this one. The m value will be larger in the third slope than the other slope. So that's how you know it's actually increasing at a faster rate. In comparison with graph C, you know that the slope is smaller, and the third slope will be smaller than the first slope. The m value will be smaller. So that's how you know the graph is decreasing over time. Okay. Then we go to example 13. So 2 women are running on the same track. One has just finished her workout and is decelerating, at first slowly and then more quickly as she comes to a complete stop. The other woman is just starting her workout and is accelerating, at first quickly and then more slowly as she reaches her target speed. So we're going to use one graph to illustrate the rates of both women. Okay, so for person 1, we know that she has just finished. So if she just finished, that means that she was already going really, really fast. So that's why she starts so high up. So once she's finished, now her rate is going to decelerate. So she's, first going slowly, more slowly, and then more quickly. So this is a part that she's decelerating more quickly. And then she stops right away, right soon after. And for the other one, we see that she's just starting, which means that her speed is 0. And she accelerates, and then more slowly. So that's why she's accelerating more slowly here. And as she reaches her target speed, so if we were to move this graph, if we were to extend it, she'd actually probably move something like this, because now she's reached her target speed. And that's how we can interpret the solutions to these 2 graphs. Perfect. Okay. So I hope this video explained a bit more about how we can represent rates of change graphically. If you have any questions, feel free to contact us on our website, passionateminds.com. And thanks for watching.